while we're setting up, it's my great pleasure to introduce Jingfeng Wang, who is also very active in this MEP community, and he's going to talk about modeling of heat fluxes over the land surface.
Thank you. Good morning, everyone. Ralph just gave a very excellent overview of the application of the MaxEnt and MaxEP theory in the study of climate. So I'm going to give you a concrete example. How do we use this theory to develop the modeling tool? So the process I'm going to model is one of the fundamental processes in the climate system, not only on Earth, on any planet, as Ralph just mentioned. It is the energy coming into the Earth's surface. For example, here we call it the RS, it's shortwave radiation, the energy input to the Earth. This energy input to the Earth system then will be converted to so-called surface heat fluxes. So part of the energy goes into evaporating water if there is water on the Earth's surface. And also part of the energy goes into heating the air. And also part of the energy will also get into the soil, heating the Earth itself. So the basic question any climatic model will answer is to how do we know how much energy goes into which of the component of the surface energy balance equation. So, because we know the energy must be conserved. Of course, if we know the total energy input into the Earth's surface, we don't know each of the component, how much it is. So we need more information. So the question is, what's the additional information to allow us to determine, given the total energy, we know each of the component of the energy balance equation described here. So again, this is E is evaporation, heat flux into the air, heat flux into the ground in this case. And this was usually been done. And don't take the equation too literally. I just use that to illustrate the concept. So usually the way this fluxes is being modeled is say we get the information of temperature. So the flux is related to temperature gradient. Here, for example, we have a sensible heat flux is from surface into the air to heating the air. It's related to the difference between the temperature of the surface and temperature of the air at some level. If we know also the turbulent flow, the characteristic turbulent flow transport, it's the same thing as for the latent heat. So here, latent heat is described by related to the transport of water vapor, because the water vapor results from the evaporating of water, which is involving the energy. The same thing is for ground heat flux. So here, the idea is to get the information of the temperature gradient. Plus some understanding of the heat transport process related to the even turbulent flow, the molecular diffusion in the soil. So we know how much energy goes into which of this heat flux component. So this is very common modeling in the climate study. And this way of called bulk transfer model has a few theoretical and technical inconvenience. One of the major difficulty is that now we do the global study. And the only information we have global coverage is from the remote sensing observation. And for remote sensing observation, it's very difficult to measure this temperature at two very close levels, close to the surface, if it's possible at all. So that would be ideal if we can get this flux, developing a model of fluxes, not based on two level, but a single level observation. The other obvious drawback is that we have these fluxes were dependent on to a close to number which has close magnitude. So we look at difference. So that will inevitably associated with tend to be have larger uncertainties in the modeling. So now we have this MaxEnt, MaxEP theoretical framework. So let's see how can that help us to developing a model of surface fluxes. So let me just give you a very quick overview of what's the theoretical framework I'm using to develop the model. So again, this is a very familiar, usual way of doing the MaxEnt analysis. So we have a variable which has n possibilities, each of it associated with a probability called pi, and then we want to find out the probability distribution based on some information in this usual constraint form as mean value of this variable, the arbitrary function of this variable. Fk here is a given constraint. So here you can call it the mean value of this arbitrary function, but the mean is not necessarily related to the sample mean as we discussed yesterday. So I viewed it as some information, prior information we have about the microscopic process that's observable, and or the value can be, I viewed as some sort of characteristic or representative information about the system we're studying. So I'm not getting into that much. I don't think I need to say more on that. Then we know the probability distribution is the so-called canonical distribution. Here Z is the partition function, and the lambda here is the Lagrangian multiplier associated with the constraint. And the maximum entropy based on this information we have, as we know, is expressed as the log the partition function plus lambda k Fk, a summation of all the information we have. So this is the well-known equation. Since the constraint, the information contained in the constraint is the same as that, is equivalent to the Lagrangian multiplier. So then these two must be related. The relation between the constraint and Lagrangian multiplier is now through this equation, which is familiar LaRhonda transformation in the thermodynamics. So it is transform one variable, one set of variable to the other. This is quite general property of this MaxEnt formalism. And then the MEP theory is a special case of this MaxEnt analysis. It's for a special case of the function here is called antisymmetric function. And then, I apologize, there's a typo here. So here's should be negative sign in front of it. It is like the variable xi can be grouped into two parts. And if you do the function is on one part is just a negative of the other. So this type of function usually can be associated with the like transport process. Say if a transport heat is a microscopic, is a macroscopic behavior, microscopic movement, transport of kinetic energy. If you reverse the velocity, you reverse heat flux. So things like that. So do you notice that if we're dealing with the antisymmetric function, then the LaRhonda transform pair becomes this. It's interesting, we're dealing with antisymmetric function, but the LaRhonda transform pair becomes somewhat symmetric, which is very interesting. And that has some important implications that help me to develop the model I'm going to discuss today. Then Dewar published a paper 2005, and just developed this idea. He introduced a function called dissipation function, also known as entropy production function for the reason pretty obvious later on as I move on. Then the LaRhonda transform form is what he called orthogonality condition here. Of course, this is understood since the lambda f constraint are equivalent. So we can express the dissipation function either in terms of constraint or in terms like Lagrange multipliers, the same thing. The orthogonality condition, which is essentially a Lagrange transform of the constraint Lagrange multiplier, turns out to be a necessary condition for this dissipation function under the additional constraint on the constraint itself. For example, we know the heat energy must be conserved. So that put a constraint on these microscopic properties we know in terms of the F variable. So what if in that situation, under certain cases, for certain cases, this Lagrange transform pair in this format implies this dissipation function will reach either minimum or maximum, depends on the constraint itself. For example, if the constraint on the constraint is a quadratic function form, we can show that the dissipation function will reach a maximum value. When this additional constraint is in the linear form like this, and we have a minimum dissipation function. So actually, Pascal and Wang has gave example how this how you use this maximum entropy production idea to get a Kirchhoff law. But today I give you another example, just showing different way of getting the Kirchhoff law, but using different constraint, and under which the dissipation function is minimized. So that laid out the general framework of developing this Fluxes model. So then what we need to do is to formulate dissipation function for the problem we're looking at, and then find the stationary point of the dissipation function, then solve for the fluxes. So that's quite simple. So I'll give you an example how that works, how this idea works. So let's look at electric circuits with two parallelly connected resistor called R1, R2. So I asked the question, given the total electric current, how does current split into two parts? You know the Kirchhoff law is easy, but we can get this using the maximum entropy production formalism. It's like this. So let's write the thermal dissipation function of the resistors when there's a current going through. So we know if it is like this, it is a current squared times the resistance. So this is the total thermal dissipation of the system. Then we minimize this dissipation function under the constraint of total current. If you do that, you introduce a Lagrange multiplier associated with this constraint, you minimize this dissipation function. What you get is just Kirchhoff law. And interestingly, the Lagrange multiplier here is the voltage of the resistor, and the voltage is the same. Meaning, so we have a parallel connected resistor, and voltage will be the same, which is obvious. So, but then we see that came from the max entropy production theory. So now we have an example. The physical meaning of the dissipation function is quite intuitive. you can divide this dissipation function by an arbitrary temperature, say equal temperature. What you get is the thermodynamic entropy production. Then you could say, well, this is minimize the thermodynamic entropy production. You get the same thing. And then the Lagrangian multiplier just the voltage. Interestingly, because there's nothing special about formulate this problem in terms of the current. You can formulate in terms of a voltage. What you get is that corresponding to the problem of two serial connected resistor. So that if you have total voltage, what's the individual voltage of the two? Then you get the same thing. It's just the voltage is proportional to the resistance. And the Lagrangian multiplier there is current, it's constant. Of course, serial resistor, the current is constant. So it is quite intuitive, yes.
I'm a little bit confused about how is it that sometimes you maximize and sometimes you minimize?
Oh, depends on the constraint. If the constraint is a quadratic, you will find out that extremum is maximum. If the constraint is linear, you will find out that extremum is minimum.
Why?
Oh, you look at the second order derivative, you find out in this case it's positive. So we can get into that math detail.
I can see that if you minimize here, you get the right answer.
Yeah.
But if it's going to be a principle of general applicability, you would like to always maximize.
Well, you better, let's better call it extremum principle instead of maximum or minimum. It's for some reason, I will just call it the maximum, but not necessarily maximum. It's extremum. So that gave us some sense how this the theory can be used to model the fluxes. So by analogy, I would write the dissipation function for the line surface energy balance system in the same similar form as the flux squared divided by some parameters. It turns out this parameter is thermal inertia. And I won't get into discussion why it's thermal inertia. I know it's thermal inertia because I know example where I can solve this problem precisely by solving the heat transfer equation. Then I found out that from there, if I solve the same problem using this approach, this idea, and this parameter must be thermal inertia. So if we formulate the dissipation function in terms of the flux squared divided by thermal inertia, then our next job is to formulate the thermal inertia, or what's thermal inertia associated with each of the fluxes. So again, the thermal inertia of the conduction of the soil is a physical property. It's equal to the density, heat capacity, and the square root of the diffusivity. And by analogy, we can do the same thing for the sensible heat flux, except here the diffusivity is eddy diffusivity. We need to model that in terms of turbulent flow. Yes. And then we do the same thing for the turbulent to the sensible heat to latent heat flux. I won't get into detail. I'll just show you what the result is. Using Morning optical similarity theory, we could get this thermal inertia for the sensible heat flux in terms of the heat flux itself. So now we have a situation where that this dissipation function is a non-quadratic in terms of the fluxes itself. So I'll go through that. Skip that. Then the thermal inertia associated latent heat flux is based on some argument, intuitive argument, will be related to the thermal inertia of the sensible heat flux with additional parameter which include effects of humidity and temperature, and also the ratio of the eddy diffusivity associated transport of heat versus transport of water vapor in the air in this simple form. So again, then we do the same thing as we do the electrical circuits case. We find out, because it's a little bit more complicated because the functional form of the dissipation function is not non-quadratic. We won't get a linear function out of it. So, but we get a simultaneous equation for the three fluxes if we do the minimization process. And here we can solve it through a numerical algorithm by the C-flux, given the input of the temperature, humidity, and given the total energy input. So we determine we get a partition of the energy balance. So now we have a model which uses only the surface variables to get the fluxes out. So I'll just show you very quickly the example here. So here is I test this using the field measurement from the Lucky Hill in Arizona, collected using the field equipment. So here you see the model prediction compared to the observation using the net radiation, temperature, humidity input from the side, and you will see this agreement is very well. I have to say, no other model can do that, using only this three variable input to get the three fluxes out. So this is the case where we're dealing with vegetated surface, and actually it's a simplification compared to bare soil. And here's a test for the vegetated surface using this MEP model of heat fluxes. And we also tested it using the remote sensing data. Also, it agrees pretty well. All right. So the conclusion is, so this is MEP. MaxEnt formalism can be used very effectively to develop modeling, develop the surface heat flux models. And again, I will emphasize this is a Bayesian inference. I won't say it in the other occasion because they're going to confuse heck lot of the audience. Usually they view it that they like the physical model. If you say your model is physical based, they like very much. If you say it's inference, they're very suspicious. But here we understand the meaning of inference. So I will stop here and answer questions.
Okay. Thank you.
Yeah, it's good to see MEP being applied to something that might affect how much food people can grow and whatever. But can you go back a slide or two? You went very there that one, yeah. You went through this quite quickly, yeah. And the data are presented here in such a way that one is sort of tempted to see the two curves as being near coincident. But what you're basically seeing is the diurnal cycle. That there's no flux, at night, and there's lots of flux during the day. Can you say how good the model really is? I mean, it looks like there's a consistent under prediction at night. And I mean, well, is this good to 20%? Is this good to 5%?
I didn't show the scatter plot shows better the agreement between these two. Here, I agree. You say that the model is significantly over predict. It depends on negative. You call it negative, the over or under relative to observation. Because this case is the measurement using eddy covariance system. As we know, eddy covariance has hard time to catch up the nighttime fluxes. Other than that, it's.
So you think the model is right because the observations are wrong?
I have more confidence in this case in the model prediction during the day because I know they're very well, and I know the eddy covariance system works not so well during nighttime. So putting these two information together, I come to the conclusion that.
Well, then you have a very nice testable prediction, do you not? That your MEP model is showing an appreciable negative flux at night.
Yeah.
And that has to be measurable somehow.
Yeah, exactly. Because at night, we know the net radiation is negative. So that negative radiation must go either the sensible heat or ground heat, because nighttime is very little evaporation. We know that. And the ground heat flux in that case agrees a lot more closer than the other term. So we have night radiation observation at night. We have quantity flux observation at night and the model. Those two agree very well. Now the MEP predicted sensible heat flux. You put them together, agree with observation very well. So the conclusion is observe the sensible heat flux at night from anti-covariance is less accurate.
Okay, a few more questions. We'll have to just ask some quick questions, thanks.
Yeah, I have a question. Do you maximize or minimize entropy of function?
Well, the maximum or minimum itself is less important. It's the stationary solution, stationary point of the dissipation function that's important. So whether it's minimum or maximum doesn't affect the answer, the solution.
So why do you call your method as the maximal entropy production?
Well, that depends your constraint. If you want to maximize, yes, for a certain constraint, you do maximize it. But in under other condition, you get minimum. Depends on the constraint, as you show. I can tell you more detail after the talk.
I just wanted to congratulate you on the correct presentation of the MEP formalism and your emphasis on the fact that it was the mathematical expectation of an arbitrary constraint function that was the information in the model, and you emphasized the fact that it was not the average of any data.
No.
So that was very well put. I appreciate that.
Isn't that obvious?
Not to everyone.
Yeah.
So just quickly, I guess we can talk about this in more detail later, but can you say what constraints went into this model?
Constraint?
So the standard model would be the Penman-Monteith equation or something.
Right.
Have you derived this, and if you have, what assumptions did you make to put into it?
Well, here is that given the information of, the question is, I'm asking is this, given the information of net radiation and temperature and humidity at one level, can we say something about fluxes? And the MaxEnt or MaxEP frameworks, formulas can give us an answer.
With no further constraints?
No further constraints. Well, you won't get it using the conventional Penman-Monteith approach, which is viewed as a physically based model. So one is physical based, one is inference. So here I'm giving you inference. This is my guess. And it turned out to be a very good guess.
Okay, just quickly.
Yes, I'm still a bit hung up on the minimum versus maximum problem. What happens if I get halfway between, so that
you may get a saddle point.
Power.
I'm sorry?
There'll be no discrimination.
You get a saddle. Is that what you mean? Because the three cases.
Yes, I suppose so.
You could have maximum, minimum, or saddle.
Yeah, okay.
And it does not affect the answer. So whether it's minimum or maximum does not affect the solution of these fluxes, the formulas. Just like the dissipation function in the electric circuit, whether it's minimum dissipation of energy and maximum dissipation, and depends on how you look at it. I didn't have time to get into that, but I do have an example where you could rephrase that problem where you have the maximum function.
I just wanted to make a couple of comments as well. We've got to be very careful with this. A number of people in the audience have picked this up about maximum and minimum EP. First of all, there's an inversion principle that seems to be happening, and there's also some pseudo min-EP and max-EP principles out there. We'll talk about these in my talk. So you've got to be very careful. Roderick Dewar's analysis, where he talks about orthogonality conditions and the dissipation function, has been shown to be incorrect. So we can't base anything on that formulation. So
I realize that.
We've got to be really very careful in how we formulate.
I see your point. I see your point.
But this is something that we can continue.
Yes.
We better go to the next speaker. Can we all thank Jingfeng for his interesting talk?